Remember, the objective we're looking at here is to tie electron configuration to the periodic table, and eventually you should be able to look at this as we do the Aufbau process and go from 1 electron to 2. You're going to see how filling up these energy levels is corresponding to increasing atomic number and the location of elements on the periodic table. So we study this. We study the order that electrons fill so that we can understand what electrons are in the outer shell. That's why we're drawing the electron dot structure, because once we know about the electrons in the outer shell, we can predict how is this atom going to react with this atom. So pictured at the left is often called the diagonal rule. It's the order that electrons fill the sublevels. Now as you look at this, the large numbers like the 1 and the 2 and the 3, those are the energy levels, the principal quantum number, the distance from the nucleus. It also is the row on the periodic table where the highest energy levels fall. So the letters represent the sublevels. S, P, D, and F are the only sublevels that we're going to talk about when we're describing the electrons in the ground state, as we are in this current process, the Aufbau process. And the small numbers, like here, 2, 6, 10, and 14, those are the maximum number of electrons we can fit into the sublevel. So if you want to know how many electrons can fit into an energy level, you just look across at the entire energy level. 2 electrons in the first energy level, 8 in the second energy level, and in the third energy level, 18, and in the fourth energy level, many more than that. And if you want to know exactly how many electrons can fit, the formula is 2n squared, where n is the principal quantum number. So for the fourth energy level, n is equal to 4. 2 times 4 squared is 4 squared is 16 times 2 is 32. 32 electrons will fit into the fourth energy level. Now, another important thing we will notice is that this diagonal rule tells us the order in which electrons fill. First of all, 1s, then 2s, 2p, 3s, 3p, 4s, and then a surprise, we go back and finish filling the third energy level. 3d fills after 4s, but before 4p, and then 5s, 4d, 5p, 6s, and then we get to 4f. So, we've been studying the Aufbau process, this building up of starting with 1 electron in helium, writing the orbital notation, the electron configuration notation, and the electron dot structure. And we've worked with this some in class, so this is familiar to you. Helium with its 2 electrons, its orbital notation, and its electron configuration notation of 1s2, and its electron dot structure, where we place those 2 electrons next to the symbol for the element. And so we learned that we're at the end of the first period, the first row on the periodic table, and we're also we have as many electrons as can fit into the first energy level, so now we're going to have to go to 2s. And we moved on to lithium with its electrons 1, 2, 3, and its electron configuration notation of 1s2, 2s1, and we only show the highest energy electrons in the dot structure, so that's only one dot for lithium. One electron, because of this, one electron. So I want to remind you here that when we go on to boron with 4 electrons, electron configuration notation 1s2, 2s2, and electron dot structure showed those 2 electrons. I want to remind you that the quantum numbers that we have been studying, this 2 is the principal quantum number, the s is the sublevel, the orbital, and the spin is represented by the up arrows and down arrows here inside the circle. So we were probably at least to boron with 5 valence electrons, and we drop those into place. Now before you go on to carbon, hold up if you're getting ahead of us here, because carbon's going to, throw something a little different at you. So these 3 electrons go into the valence electron dot structure, and we showed 2 of them paired, just like those 2, and we showed 2 of them, one of them by itself, just like that. And so the electron dot structure is tied closely to the orbital notation. So for carbon with 6 electrons, it goes something like this. We have to be sure we draw all of the possible orbitals. Remember, the p can have 3 orbitals, the p sublevel, so we have to draw them all. And notice we have something called Hund's rule, H-U-N-D apostrophe S. Hund's rule says this: these electrons will go into separate orbitals in the same energy level before they begin to pair. And you can see this in the orbital notation and in the dot structure, because when we draw the dot structure for carbon, we're going to show these 2 electrons paired and these 2 electrons by themselves on different sides of the symbol. The electron configuration notation for carbon is just going to be 1s2, 2s2, 2p6. Did I say 2p6? 2p2, because there's only 2 electrons in the 2p, and you have the electron dot structure already, because the electron dot structure only shows the highest energy level electrons. So after carbon is atomic number 6. Atomic number 6 is neon. Nitrogen. It's getting too late. Okay. So I'm going to draw in the orbital for the 1s, the orbital for the 2s, and then I'm going to remember 2p, because it's a p sublevel. P sublevels have 3 orbitals. Now I'm going to drop in the 7 electrons. Where are they going to go? Do you remember? Hund's rule says we're going to have 1, 2, 3, 4, and then 5, 6, 7, with all of those in separate orbitals. So the electron configuration notation is going to be 1s2, 2s2, 2p3. Got it right that time. And in our dot structure, we're going to put the electrons in the highest energy level. And so in our dot structure, we're going to put nitrogen and 1, 2, 3, 4, 5 valence electrons. Do you see why these valence electrons are by themselves? Atomic number 8 is next, and you're getting these all written down, right? The Aufbau process, the building up process. Atomic number 8 is oxygen. And we drop in 8 valence electrons. You have that orbital notation about done? The electron configuration notation is going to be 1s2, 2s2, 2p, 1, 2, 3, 4. And the electron dot structure is going to include the electrons of the 2s and the electrons of the 2p. So we're going to write the symbol, 2 electrons paired, 2 electrons paired, and 2 electrons by themselves for a total of 6 valence electrons around oxygen. If you need to go look at this PowerPoint is on the website. It's in the last half of the PowerPoint that's there for notes. Okay, fluorine. We're going to draw our orbital notation. Draw all our orbitals just like we have been. And we're going to drop in the electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 valence electrons. And the electron configuration notation is going to be 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 2p5. Now I can also count these up and make sure I have 9 electrons by doing 2, 4 plus 5 is 9 electrons, the atomic number of fluorine. And the dot structure is going to include these 7 electrons. So we're going to have fluorine 1, 2, 3, 4, 5, 6, 7 valence electrons. Now we're going to finish out this row of the periodic table with atomic number 10, neon. You'll notice the S and P sublevel are now filled. The electron configuration notation looks like this, and the electron dot structure looks like this. Now it's important to notice we are in the second energy level is now filled. We're at the end of the second row on the periodic table, and this is the end of this video. We'll continue in the next video.